what do you say? What's it? No, that's the mean value theorem. F of x must be continuous. Doesn't have to be differentiable. Okay, guys? The mean value theorem has to be differentiable. We're just talking about the max min existence there. My function must be continuous and on a closed interval, right? Those are the conditions. So if I have a continuous function on a closed interval, then that what? Guarantees. It's a promise. That f of x will have both a maximum value and a minimum value. So if you have a continuous function and it's on a closed interval and you're asked to find the maximum or minimum value, you're guaranteed it's going to happen. Where will it occur? At where? Endpoints. So these are called critical points. So that's the endpoints. Where else might you have a max or min? When the derivative is 0 or the derivative is undefined. And how do I know then if I have a max or what the maximum and minimum value is? Okay? So what you do is you take your critical points and substitute those critical points not into the derivative but into the function. Back into the function. And I guarantee you will find both a maximum and minimum. Just look at the values. And you will find. So that's the easy way. There's other ways to do this. Now remember, we're not looking for the where, we're looking for the what. Values of f of x. So it's a three-step process. First, you make sure this applies. It's got a continuous function closed interval. So I know that if I'm on the test that says find the point that's furthest to the right, that's a maximum. And they give me a closed interval, and I'm going, okay, this is going to be easy. All I have to do is look for where my derivative is 0, where my derivative is undefined. That's the only calculus. And then I'll evaluate the endpoints and each of these x coordinates that give me those conditions in my function, and I'll just take the maximum value and I'll take the smallest value. That's all. Yes, it's also called the extreme, I guess they call it extreme value theorem. Okay, that was 4.1. 4.2 did problems that had increasing and decreasing functions. I think what else we had in there. Not that much. What if we don't have a closed interval, or if you don't have a continuous function? How are we going to find that the function has a maximum or minimum value? We have to have another test. We can graph, but if I don't have a graphing calculator, I'm in trouble. Will there be any guarantees? No. For example, if I have a parabola on an open interval forever, there is no max, is there? But there is a minimum, and the minimum is at the vertex. Did you guys ever learn that the vertex occurs at x equals the opposite of b over 2a, given that f of x is equal to ax squared plus bx plus c? Well, that's a nice one to know, especially on the SAT and ACT. Because it's easy to find the vertex. You can find the intercepts and then just find halfway, or you can just use opposite of b over 2a. What's true about the derivative at this vertex? Why does this work? What's true about the slope here? It's what? It's 0. If anybody can't see, you can take my iPad. So what's f prime? Let's take the derivative and set it equal to 0. It's 2ax plus b. And if I set that equal to 0 and I solve for x, I'll subtract b from both sides. So minus b equals 2ax, and I'll solve for x by dividing by 2a. And there's that little formula. That's where it comes from. I think that's cool. Well, it's nice to know that the vertex form is minus b over 2a if you have to take tests. If you're done with your tests, SATs, ACTs, then it's not that critical, but it really would help you. You probably had to find a vertex of a parabola someplace. That's the easy way. And then to find the y-coordinate, I'll have to evaluate my function at that point. It looks ugly, so I'm not going to do it. Okay. There are tests to find local max and mins. And the first one is called the first derivative test. And that is it all written out. I'm going to make it simpler than that. Yeah, because that looks... It looks complicated. Here's my derivative line. You're going to need a line. You're going to have to show the testing, but this does not count for your points on the exam. If this is your C value, and let's say it's 0, and this is positive, and this is negative, and your derivative, what does this tell you your function's doing?
The line.
No. If f prime...
Oh, it means it's going like this.
It's increasing, right? Now, if it goes to 0, that means it's got to increase nicely. You're not going to have a sharp corner. So if it's increasing, it's going to have to be this form. So my function's increasing, it zeroes out, and then what does it do? Decreases. So f prime changes from positive to negative. What do we have here, a max or a min? It's a max. I don't memorize all that. I just look at the picture. It's so easy. It's much easier to do that. Okay, and we'll do an example. We'll get through all this stuff and then we'll do a problem. Okay, there's my f prime again. And here's my C value. If this is negative and this is positive, then what's happening to my function? Remember, if f prime is less than 0, then f of x is decreasing. It's getting smaller. So it's going to get smaller, it's going to go to 0, then it's going to increase. So it's at a max or min. And you would say f prime goes from minus to positive. Now, I have problems remembering that, so I just draw the picture. I previewed it. It's all it is. It's the first derivative test. Second derivative test we're going to do tomorrow, not today. And they can force you to use the second derivative test. I always have to forget the problems, but you may have to use it. This is the most widely used one. And now that doesn't give me an absolute max, it gives me a local max. These are local or relative. It could be the absolute, but there's no guarantee. If I have a closed interval and a continuous function, then there's a guarantee. You know, and so you can look at this. Is this ever going to turn around again? And let's say this is what my function's doing. It's decreasing, increasing. Is it ever going to turn around again? It's the only critical point I have. No. So this is the absolute minimum. Now, when they ask you for the absolute maximum or absolute minimum, there's not going to be a trick there. They're not going to try to trick you. We'll be doing optimization problems. I'm not going to put a lot of time into it because it's not really hit on that hard on the exam. Watch me be wrong. Okay, this is at the bottom of your sheet. Actually, I could just get it out of there. Oh, nice. It's at the bottom of the second page. So we'll talk about that later. Now, what do I mean by concavity?
Concave.
What is this? Concave what? Up. This is concave up, like a cup. Concave up. You might have to get a piece of paper out. Sorry, because we messed up. If you actually, you have an extra, if you get out section 4.23, day 2, you have a whole extra piece of paper on the back. This is the gold one. It's the day 2 one. Well, we're going to do concavity, we're going to do a problem. That's right. Jason's ahead of me. This is concave down like a frown. Now, my University of Minnesota students didn't like the concave up like a cup, so they'd say concave up like a duck. Because, you know, a duck's tail.
That sounds like way more.
I know. I thought they were silly. Down like a frown. That's freshman in college.
Wait, so the same thing? This other paper that you were talking about.
This is up. You're happy. It's the, whether it's going to hold water or do this. Those are the only 2 choices. Like a frown. So let's look at it. So if I have this, this is concave up, right? And then it switches concavity. That's where these get tricky when we do these. And then it stays concave down. And then it goes concave up. It's the shape of the curve. Whether it's going to hold water or if it's going to be upside down. That's all it is. So how do I know what the concavity is? Well, there's a couple ways to do it. I like the easy way. What's true about your derivatives here? This is negative, negative, then it becomes 0, and then it becomes positive. So there's 2 ways to say it. F prime is increasing if it's concave up. I always draw the picture. Because they're going to ask you, because you're going to find you're going to find where the concavity is so you can draw pictures. If f prime is increasing, what's true about the second derivative? What's true about the slopes here? If they're increasing, then f double prime is positive. So when you justify your answers, you may use either one. Personally, I like using the second derivative. Because if you're concave up, you're happy, the second derivative is positive. So what about this one? What's true about the derivatives? That's a positive 2, positive 1, 1/2, 0, it becomes negative, so what's true about f prime? It's decreasing, so that's concave down, or what's true about the second derivative? It's negative, because you're down, you're negative today. I prefer to do it this way, but both answers are correct. No, because I'm finding the slope between the slopes here. Second derivative, it's just that it's going to be giving negative. You don't. You just say the second derivative, because it's concave down, the second derivative will be negative. Let's do a problem. Now, before we do that, one more word. Inflection points. Where the concavity changes, those are called inflection points. It's a single point. It's a point where the concavity changes. But that's not proof. It's what it is. That's a definition of what an inflection point is. So if they ask you on the exam to find the inflection points and justify your response, you can't say the concavity changes. That's what an inflection point is. That's not proof. What would happen to your second derivative here? It's concave up. What's the second derivative here? Positive. Goes concave down. Negative. Concavity changes when the second derivative changes sign. So those are the points. How do you prove it? F double prime changes sign. You don't have to say positive, negative, negative, positive. That's sufficient. All you have to do is say it changes sign. So we got a couple problems to work. Find my other one. And really, that's all there is in section 4.3, plus the second derivative test, but we'll do that tomorrow. I'll save something for tomorrow. So I have an example here. And the question in the book, I don't remember what the questions are. Find the intervals where the function is increasing, decreasing, find relative max and mins, find inflection points. I should have said, find concavity. Well, you will find the concavity. Cut that out. Okay, are you ready? You know what it looks like, right? Cubic. Yeah. So it's going to do something like this, probably. So I get a concavity change here. I don't know where that is. But this is concave down. That's concave up. That looks like a local max and a local min. I better put local in there. Where are they? Well, let's do the problem. So how are you going to find it? I don't have endpoints now. So how do you find where the function's increasing and decreasing? The derivative. So let's find the derivative. I didn't make it too horrible. So what's y prime equal to? The algebra that gets us more than anything. 3x squared minus 12. And I want to know where that's going to be positive and negative. So I want to find the zeros. So what can I factor out of this? 3. And I'm left with x squared minus 4. Yeah, that can be factored. What's it going to factor to be? Not 4, but 2.
Oh, that's what I meant.
I figured that's what you meant. Okay, I'm going to do a test line, although that is not enough to prove if you have a max min or anything like that. Okay, so my critical points are at -2 and 2. You want me just to test regions?
Yes.
Okay, what's the easiest one to test? 0. I always do easy first. So 0, if I put 0 in here, I'm going to get a +2 times a -2. So it's what? Negative. And I also like to write zeros in here. Because if it's undefined and it's a continuous function, it's going to be a sharp corner or a vertical tangent. Gives me an idea what I'm looking for. But if I have zeros, then I know it's going to be smooth like this curve right here. Derivative. This is f prime. To the right, you mean? I put in 10, that's positive. I put in -10, it's also positive. But you know what? I knew that because this is a parabola, and it would look like this. My parabola here, my derivative, is positive there, negative here, and positive. So, okay, where's it increasing? This is just like the homework. From -infinity to where? -2. And then from 2 to infinity. And it's decreasing between what? -2 and 2. Now on the exam, they're not going to probably give you the function. They'll give you information about the derivative. And then you just go from there and try and draw pictures. Okay. Now let's find the max and mins. Because what's true about my function? Not the derivative, but what's true about the function here? The derivative is positive, so the function is what? Yes. We already said it's increasing, right? So it increases, it zeroes out, and then you told me it starts to decrease till it zeroes out and increases. And I don't know exactly where my graph is. Oh, darn it. Got it separated. I could shift it up and down. I don't really know where it is. Only way I'm going to know is by evaluating my function at these points. So, what happens at -2? Do I have a max or min? At x equals -2, f of x has a max, right? How do you know? Okay, you have to say why you know it's max. And you can't just go by the sign chart. I changed that a few years ago. You actually have to say f prime does what? Goes from positive to negative. If what I've written there is enough. It's sufficient. is B, finding relatives, max and mins. You're right. What happens at positive 2? It's a minimum. X equals 2, f of x, these are all locals, has a minimum. How do I know that? Oh, it's f prime goes from negative to positive. Nice. That wasn't too bad. So it's just a little bit more than what we did yesterday, but I do want to find inflection points. I need to find concavity. So what's true? What do I have to do that? Find the what? Second derivative. This will be C. So, okay, there's my y prime. I'm going to rewrite it because I'm going to slide my board. It's 3x squared minus 12. And now I need to take the derivative again. You should be ahead of me. What's the derivative of 3x squared? 6x. Okay? Thank you. And now I'm going to look for the zeros because that's a candidate for an inflection point. But the second derivative has to change sign there. Where is that? At x equals 0. So I'm going to draw my little line again. There's a way to reorganize that. And here's my 0. And it turns out to be nice. That's y double prime. And when I put in a positive number, what's true about the second derivative? It's positive. When I put in a negative, it's negative. So this is a single point. At x equals 0, there's an inflection point. And I even know where that is on my graph. So what's happening on the left side? If the second derivative is negative, then the function is concave down. If the second derivative is positive, it's concave up. How do I know that's an inflection point? Because what happened to the second derivative? Second derivative changes sign. Now, that's a lot of stuff you guys have to learn. So if you do your homework, you do some repetitive stuff, it might sink in. Because you got to put it all together in May. And, I got a good picture there. There it is. Looks like it's at 0. X equals 0. It looks like it changed concavity right there. And I think that was it. I have an empty spot here. Okay? Well, I'm going to give you a worksheet to work on and see if you can find the intervals where it's increasing, decreasing. Now, when you do inflection points, it's a single point. It has to be positive on one side, negative on the other side, a single point. Can't be a line. What helps? They want you to draw a sketch of what that function might look like. Sketch a graph of the function has these properties. This function right here. They didn't tell you what the function was, did they? Well, I'm going to draw a little line graph just because it helps me do it. You don't have to, but that all looks the same to me. Does it look the same to you? I'm looking at those inequality symbols, hoping I even wrote them down correctly. Okay, so my critical point here looks like it's 2. And this is f prime. My derivative is positive when x is smaller than 2. Did I do that right? It's very easy for me to do it wrong. And it's negative for x greater than 2. F prime of 2 is 0. If f prime is positive, that's positive, and this is negative. If f prime is greater than 0, then it's positive. Right. There's a lot of stuff to look at. And so I want to graph this, and it tells me what? It tells me that f of 2 is 3. So that tells me where this is going to be. And it tells me that the slope there is 0. I don't know much more than that. I just know it's increasing here. and then decreasing. Somebody said I'm going to have a parabola. I have no idea where it crosses the x-axis. Just to do a sketch. All you have to do. B is very similar. Should we try C? Because that looks a little different. And the thing is, you have to really think about this. F prime of x is less than 0 everywhere except at 2. Now, if the first derivative is less than 0, it means it's negative, which means f is what? See, f prime is negative, so f is decreasing. So I'll just do a little sketch. They get complicated. This is not complicated yet. Ooh, sorry. F of 2 is 3, right? Slope it there is 3, and it's always decreasing. So it's going to come in. I don't know anything more than that, but it's going to zero out here, and then... Now, it can't be a sharp corner. Concavity has to change. Because let's try it a different way. Because let's say it's decreasing... I'm trying to figure out how to do it. It's decreasing this way. I guess I could do this. And again, what would this have to look like? Look like that, right? You can't have it come in like this. It's just not going to work. What I want to do, this one. Because what's true with the derivative here on that red one? It's not 0, right? It doesn't exist. So anytime I have the derivative being 0, I know it's going to be smooth. I don't even need to do the second derivative test, really. I know it's going to change concavity there. Okay, do you think you got enough to finish that problem? Yeah, you got to try those. Other ones? Now, what I would do with 41 is I would just sort it all out, just like put it on a line graph like that again. Any questions on the mean value theorem? Well, it's not too bad. About 4.3. Let's see. Questions 1 through 6 use the first derivative test to determine local extreme values, max, mins, and identify any absolute ones. You actually have to graph it, but you know what number 1 looks like. It's a parabola. So that's all you're going to do. Yeah?
When they say first derivative,
Right. If the first derivative is changing sign. What's the first problem I assigned? Any other assignment sheet? Number 1. Let's do the first problem together. Does that sound okay? Okay, this is section 4.3. This is problem 1. Y equals x squared minus x minus 1. And I want to know if I have any local max or mins. And I know I do because I have a parabola, right? We know that. But we're going to pretend we don't know it. And so what's y prime? 2x minus 1. And my critical points, my places I'm going to look for max mins, is when the derivative is 0 or undefined. Well, it's never undefined. That's a nice function. So adding 1 to both sides, and then dividing by 2, x equals 1/2. And then I'm going to have to do a line graph. Well, you don't have to, by the way. You can just figure it out, but I highly recommend it, to tell you the truth. Okay, here's my critical point at 1/2. My derivative at 1/2 is 0. That tells me if it's undefined, then I got a sharp corner or vertical tangent. Something else is going on. Okay, so here's my derivative equation. If I try a number to the right, like 10, is that positive or negative? And if I try a number like negative 10, then this will be negative. I know it's a line, so that's what's happening. So what does that tell you about your function? This one, f is what? decreasing, and what's happening here? F is increasing. So I can quickly draw a little graph. It's going to be decreasing, then increasing. It never turns around again. So at x equals a half, I have, do I have a local or global? Okay, it's also a local, but yes, global. Minimum. Is there a global maximum? No. It never turns around again. I'd have to have more sign changes up here. That's all it's asking to do in problem 1. That's not too bad, is it? I think it's too bad. And then the next set, after that, it says use the concavity test to find where the function's concave up or concave down. So you're going to have to do 2 derivatives. 7 looks easier than 10. Okay. And then you have some piecewise graphs. Did I say 11? Okay, that's a good one. Yes, let's do a piecewise one. Then tomorrow we'll do the second derivative test, and we'll do that activity, and you'll have time to work on work. Because the second derivative test doesn't take that long. Okay, this is... No, we didn't do second derivative test. No, we didn't do second derivatives yesterday. We only did first. Yeah, no, it's the same. Okay, the piecewise ones are kind of scary. I just added to it today. I just said it's increasing, decreasing yesterday. That's all we did. And today we said we could show maximums. That like me.
And you didn't draw it like positive and then negative and then
It depends on the function. If the first order is positive, it's increasing. First order is negative, it's decreasing. Same thing. Well, let's look at this one. Let's look at the first derivative here. Now, let's do it this way. Okay, what's the derivative here? 2 for x less than 1. And what's this? Negative 2x for x greater than or equal to 1. That's the first derivative. So the first derivative is positive here, which means it's always increasing. But that one's a little different. Where is the problem going to be on this graph? 2x and 2 minus x squared is not a problem. They're both beautiful graphs. Where is the problem? When x is getting close to 1. Is the function continuous? Okay, so it's not even continuous there. So I guess what I can't do then? I can't have the derivative there either. Right? If it's not continuous, it can't have a derivative. So this is not continuous because f of 1 is equal to 2 minus 1, which is 1, and the limit from the left side, as x approaches 1, of 2x is equal to 2. So if you wanted to graph it, you could. Now, does a line have concavity? Oh, well, it'll work. Not great. Well, let's just plot this. When x equals 0, what's the y value? 0. When x equals 1, it doesn't get to 1, but it gets pretty close. X is equal to 2. So this is looking like this. Does a line have concavity? No. They don't have concavity. But the next one, now when x is equal to 1, we are where? We're at 1, aren't we? So it's here. When x is equal to 2, I'm going to get 2 minus 4, so I'm going to be at negative 2. Did I do it right? And so it's going to be coming down like this. Okay, so what did they ask me on this question? I forgot. It says, find where the function's concave up and concave down. So let's look at the second derivative. What's the second derivative here? What's the second derivative on the left side? 0. So it's neither for x less than 1. And on the right side, what is it? Negative 2. So you can see I didn't write. It's concave down on that side. So f of x is concave down from negative 2. In second derivative tests, we always leave them open. So just leave first and second derivative open, and then you don't have to remember. To infinity. Okay? Why is it concave down? Because f double prime is less than 0. I have to say that. Second derivative means you're concave. Negative means you're concave down like a frown. Because I have to show the calculus. This is an easy one. They're not always easy. If you look at some of the other problems, like number 7 and 8, they're not easy. They're cubics and a quartic, so I don't know where they're concave down and up. And number 19 is a rational function, so it's even worse. I hope we're not doing 19, because if we are, don't. That's good, because that's a stupid problem. You have to use the quotient rule twice, and it gets pretty ugly. Now, why do something so hard? Okay. And I said you should probably get through problem 20. And you could even do 21, 22. There's really not that much stuff here. And we'll do second derivative test tomorrow, which starts on 33. Any other questions out of your homework, or do you want me just to help you individually? Okay, perfect.